Okay, we're going to find out if this sequence converges or diverges. We have the limit as n approaches infinity of 1 plus 2 over n to the n. So it's the limit as n approaches infinity because that's how we find out if this converges or diverges. Need a better marker. The limit as n approaches infinity of this thing is how we find out if it actually converges or diverges. So with this one, it's really quite tricky because there's several little tricks you have to use. One of them is that you have to use the natural log on both sides because you have an exponent here which is just a variable. And whenever you have an exponent outside like this, you could use the natural log property that whatever the exponent is can be brought over here and multiplied to the natural log. So let's do that. Let's equalize this to some variable x, because if we take the natural log over here, we have to take the natural log over here. So let's say the natural log of x equals the limit as n approaches infinity of the natural log of this thing here. And so remember, the reason we're taking the natural log is because we have this power here. And it's really the only thing we can do as far as I see it. So we got to bring that down. The limit as n approaches infinity of n times the natural log of 1 plus 2 over n equals the natural log of x, not just x. So now there's another trick, and if you saw one of my other videos, whenever you have n multiplied and you've got 1 over n inside, you have to get this into 1 over n form and change the limit from n approaches infinity to n approaches 0. So that's what we're going to do here. We've got the limit as n approaches infinity. We're going to leave it for now, just so I can show you. This is 1 over n, which is, if you want this to be 1 over n, because we have 1 over n here and we have 1 over n here, then we would have to divide this, right? So this 1 over n has to be in the denominator so that it could be equivalent to just multiplying by n. Natural log of 1 plus 2 over n, and this would be an equivalent way to write it, 1 over n. Now we have 1 over n here, and we've got 1 over n in here by just factoring out that 2. This is a 2, of course, but you could just factor that out. It's just some number. It doesn't make a difference to having 1 over n. So let's do that. Let's do that. Let's bring that up here and see what we get. So we've got the natural log of 1 plus, and then we factor out that 2, and we've got 1 over n. And this is all 1 over n. We're taking the limit as n approaches infinity, and this is the natural log of x. So now our question here is, what happens when we actually let this go to infinity? If we actually let this go to infinity, this right here is going to go to 0. And this right here is going to go to 0. So that means that this entire thing, which is when you apply the limit as n goes to infinity, that entire thing goes to 0, and that entire thing goes to 0. And they are the same. They are the same term. So we could say this is x, and this is x. And now x goes to 0. So that's how we do this one. That was a little tricky, but from here on, it's easy. From here on, it's just what you would normally do when solving these things. So after having done the most difficult steps, now we can try and take this limit. So we've got 0 here in the denominator, and over here we got the natural log of 1, which is 0. We've got 0 over 0. That's telling us that we could use L'Hopital's rule. L'Hopital's rule tells us that we could take the derivative of the numerator and the derivative of the denominator. Whenever we have 0 over 0, whenever we have infinity over infinity, we could use L'Hopital's rule. So what is the derivative of this thing here? The derivative would be, by the chain rule, you multiply what's inside, which would be the derivative of what's inside, which would be 2 in this case, which would be 2, and we multiply by the derivative of the entire thing, which in this case is 1 plus 2x. Because remember, with the derivative of the natural log, it's just whatever you have here under 1. So this is the derivative of the top portion over the derivative of the bottom portion, which is just 1. Anything divided by 1 is just itself. So this is what we have now. Now we could take the limit as x approaches 0 of this. Approaches 0, not infinity, because we switch the limits. We put in 0 here, we get 2. We get 2, but remember, that's not our answer. The sequence doesn't converge to 2 because we had the natural log of x equals this. The natural log of x equals 2. So how do we solve this? We solve this by realizing that the natural log of x has a base of e. E to the power of 2 equals x. E to the power of 2 equals x. And remember, x was our original sequence. So our sequence, a subscript n, and we can put the little curly braces here, our sequence converges to e squared.